am only going to worry about chapter 3 on the test. I am not going to worry about anything on chapter 4. So chapter 3 is on the test only. Because I got to get these tests made up. So, but that's where that's going to stand. So test is only going to be over chapter 3. Which means I got to get a hold of Lee, Kyle, and Kayla about how to do the test. Probably be Monday of next week. Because that's going to, but I will get, and I will have, Robin, I will have the tests over. I'll put them on the shuttle tomorrow.
Okay, I'll make sure it's.
Yeah, so that's because I'll be around on Wednesday, but I have a 7 a.m. flight on Thursday.
Okay.
So that's where that one is. So chapter 3 for this one. I will not be on campus on Thursday. I will not be on campus on Friday. And then we've got next week, and then, things, I'm going to warn you guys, between the next 3 weeks are going to go by fast, and that puts us at spring break. And if you thought that goes by fast, the month of April goes by really fast.
Then we graduate.
Then you guys graduate, and then I get to see several of you in the next time for dynamics. So if you're taking dynamics with me, we need to get you scheduled if you haven't already been scheduled. So because dynamics, because I will tell you that you want to take dynamics before you go to OSU. So even if you're going to OSU or you're going to the Bell program or whichever, if you have to have dynamics, although I think you may not have to have dynamics. Because if he's taking chem, a chemical engineering, may not have to have Charles here.
Still got an extra.
Charles.
It's like dynamics or extra thermal.
I'll take extra thermal.
Yeah.
Are you sure?
So, however, I will tell you dynamics does help all the way around. And if you're thinking of chemical engineering for the refineries, dynamics for power, for rotating equipment is a good thing to have.
Okay.
So, it's just one of those, but for, if you haven't scheduled for dynamics, it's time to get in there so that we can get that done.
Early?
Huh?
Is that late?
It's early. Yeah, everything's early. I am not teaching at all late this summer. I am actually doing some other stuff this summer.
Our physics was Monday through Thursdays.
Dynamics is the same way. Except I do more Zoom in that one because I have a lot of people that are on internships. So I work around internships. But that class does start then. All right, so we're starting chapter 4 today. I will hopefully, I worked this weekend. I got a lot of stuff done, but I didn't get what I wanted to get done, as that normally happens. So I have not checked the homeworks for chapter 4. Also, just to make you all aware that the week after spring break, I will not be here Monday through Wednesday because that's the American Chemical Society meeting. So it's going to be entertainment again. This is the first time in a while that the ACS was not during spring break. So, which allowed me to do something.
Monday and Thursday?
Do what?
Monday and Wednesday?
Monday and Wednesday after spring break, I won't be here, but we will probably have a test or a quiz on the Wednesday.
Okay.
To accommodate.
Okay.
So,
Is incur before or after spring break?
incurs after spring break. And I think it's like I want to say you guys won't be here the Tuesday through the Friday of that week after spring break.
Okay, so we'll have to take that quiz before.
Yeah, you have to take the quiz before or after. Yeah, so. All right, so chapter 4, remember a couple of things. One is for our conditions of equilibrium. I've got things spelled right. We've been doing some of the forces equals 0. And this goes to mass times my acceleration. Brandon. There you go. mass times acceleration, so that it implied that acceleration was equal to 0, which means I could be at a constant velocity or I could be at steady state. And then we said in physics, we talked about the sum of the torques equals 0, and that's my moment of inertia times my angular acceleration. And remember that if we went to work was force dot product distance, so that was Newton meters, and that was a joule. When we did this is torque was equal, and I'm going to write it differently. It was the cross product of the distance times the force, and that was actually a Newton meter, and that's not a joule. And what's really weird is in English, or in the SI system, we actually say Newton meters, but in the English system, we actually call this foot pounds, which makes a heck of a lot more sense than doing Newton meters. Because this is putting it in the right order, and it's helping us with our cross product. The other thing about this is if I've got, so this is the z direction, this is the y direction, and this is my x direction. If I have some vector and I'm applying a force, so this is my r vector, and this is my force vector, we've got the right-hand rule that says that I've got torque is acting upwards in the z direction, which is why I have to worry about the order here, because I got to use the right-hand rule. Okay? I got to use the right-hand rule. So if we're doing this, so if I have my wrench, so here's my hex nut, and I've got a wrench applied to it. We know that the maximum torque is going to occur if I am applying it in that direction. And if we did this in terms of torque, this would be RF sine of the angle. And if I'm looking at this, so this is my R, this is my force, and that's my angle. And we know that if sine is equal to 1, I'm going to be at my maximum. Now that's the physics side of things. Okay? That's the physics side of things. So let's kind of look at what's happening in the real world, because we're not going to use torque. We're going to use something called a moment. And the moment is still going to have direction associated with it, but we're going to actually set up our problem so that we're dealing with that maximum most of the time. Okay? We're going to set that up so that we do it. So if I have a sine and it's hanging down, okay, we know it's acting through the center of mass, right? Okay, we've got tension in the strings, and usually that's where we've left it. But we also have a bracket over here. And Newton, one of Newton's laws for every action, there's an equal but opposite reaction. I've got a force that's coming from the wall, and I have a force that's coming from the pole. Luckily, in this case, right, things are going to cancel each other out from that perspective. And I have a force that's acting on this bracket so that the sign doesn't go like that. Not only am I in the summation of the forces has to equal 0, the summation of the moments have got to equal 0. Otherwise, it's going to rotate and it's going to fall down. So we've been doing our force diagrams, but we haven't been accounting for these right here. So we've got to have something at A that's counteracting this at R. So I have a force that's applying down in R, I've got a torque. Okay, I've got a torque. And I've got to worry about it. Okay? And we are going to use these things. If it's counterclockwise, it's positive. If it's clockwise, it's negative. Because if I'm doing my torque this way, it's going into the board. If I do my torque that way, it's coming out of the board. So we have that, and our sign is going to fall that we end up with. So we're going to start defining moments. We're going to start defining moments. So a moment is a force, and we're looking at it with a distance. And we're going to call something a moment arm. So this is going to be my moment. We're going to end up doing force distance. And the moment arm is when the force is applied perpendicular to D. Okay? The force is applied perpendicular to D. And we're going to find that moments come in pairs. And we're going to find that moments come in pairs. So, fortuitous enough, in my notes even, we're going to talk about an Allen wrench. So I have my little bolt, right? And I have my little tool that's there. I'm going to apply a turn to that. We're going to apply a force that can look at it. So we're going to do this. And so what happens is, if my force is equal to 2 newtons, and we're applying at the edge of this, which is at 1 centimeter, or 0.00, that's not what I want, 0.01, the moment, at least the magnitude of the moment, is going to be 2 newtons, 0.01, it's going to end up being 0.02 newton meters. Nothing fancy schmancy. We can do other things that have moments. So I have a lever. This is 0.75 meters. I'm going to apply a force at the top of 12 newtons. The moment is going to be 12 newtons, 0.75 meters. It's going to give me 9 newton meters. I'm going to skip that for a second. So we just defined moments, but now I want to come back and I want to look at cross products.
direction be in the y in that example? Because our course is in the x, so it'd be perpendicular, right?
Perpendicular, if I'm applying the force, it's gonna be into the page.
Okay. I see.
Right-hand rule, into the page. Okay, so let's take a step back and let's look at some vectors. All right. So if I have my three vectors, and this is vector A, this is vector B, and this is vector C. C is equal to A cross B. And when we're in Cartesian coordinates, I cross I is equal to 0. J cross J is equal to 0. K cross K is equal to 0. If you think about that, here's my force and there's my lever arm. The sine of the angle is equal to 0. Okay? But we get that I cross J is equal to K. And we get J cross K is equal to I. And we get K cross I is equal to J. But J cross I is equal to minus K based on the right-hand rule. And K cross J is equal to minus I, again, based on the right-hand rule. And I cross K is equal to minus J. So when we look at our laws of operation, we can't do the same things that we did with a dot product. A cross B is equal to negative B cross A. I can still have a commutative rule. This is equal to A cross B, or it's equal to A. Okay, that still works. I still can do A cross B plus D. That can be A cross B plus A cross D. That still works. So all that still works. All right, so I'm going to do the gory detail here. I'm going to get a different pen so that I can write a little better. So I'm going to do A cross B in its gory detail. So I'm going to have AXI plus AYJ plus AZK cross product BXI plus BYJ plus BZK. All right, so we're gonna start with AX each time. So this is gonna be AX BX I cross I plus AX BY I cross J plus AX BZ, and this is I cross K. Okay? This is AY BX I, or J cross I plus AY BY J cross J plus AZ, AY, BZ, J cross K. And then I get AZ, BX, K cross I plus AZ, B, Y, K cross J plus AZ, BZ, K cross K. Okay. I cross I, J cross J, K cross K are all equal 0. So that's 0, that's 0, that's 0. I cross J is plus 1. I cross K, this is 1, K. This one is minus J. J cross I is minus K. J cross K is a positive I. K cross I is a positive J. K cross J is a minus I. That comes from this right here. So, if I am looking at the I and the J and the K, this is, I get, go ahead and put this in here. I get AXBY. This is a minus J, so this is a minus AXBZ. I got a minus K, that's an AYBX. I have a positive I, which is an AYBZ. I have a positive J, which is an AZBX. And I have a negative IAZBY. Now, if I go ahead and make this a negative, this becomes AZBX. And this, no, that's the wrong one. That becomes AXBZ minus AZBX. I'm putting in the negative there on purpose, because that gets us to our cross products that we can do this way. AX or AB is equal to IJK AX AY AZ, and this is BX BY BZ. And for I, what we do equals AYBZ minus AZBY. And we end up doing the same thing for each of the other ones, but the right-hand rule will allow us to do it. And so what we do is we do cross BX is gonna equal AY, AZ, BY, BZ, I minus AX, AZ, BX, BZ, J plus AX, AY, BX, BY, K. And hopefully we've seen that before. Right? Hopefully we've seen that before. And if you still have the same version of the calculus text that people had a couple years ago, it's page 792 in your calculus text. It's also in your algebra book. It's the determinant form. It's Cramer's rule. Stuff we saw last week, except we applied it a little differently. Make sense? Nothing new?
I always thought those was kind of easy, you just gotta remember the negative.
You gotta remember the negative, and when you get the bigger ones, then the negative comes into play. So now, if we look at this, this is our moment. It's equal to R cross F. And we're gonna be able to use vectors to help us out. Okay, we're going to be able to use vectors that help us out. So let me see if I got a good problem to start with. We'll start with this one. All right. So we got a lever arm. We're told that the pivot point, this is 1.5 meters, and we're told that the entire distance for this is 9 meters. We're going to apply a force where this is X. And we're going to use this to be D. And this is going to be point A, our pivot point. And we want to determine the moment at A as a function of X and the angle theta, and theta is going to be this angle right there. And we're given some constraints. Okay, we're given some constraints that theta is going to be greater than or equal to 0 and greater than or less than 90 degrees. And we're given that X can be up to 5 meters. So D is going to equal 9 minus 1.5 plus X. So D all right, D, right? Oh, this is D. There we go. That's D. I was going something's not right. 7.5 plus X. And we're gonna hang off a mass of 120 kilograms at the end. So our situation is this. We have a lever arm R and a force being applied here. And so we can have a theta 1 is equal to 90 degrees plus whatever theta that we have. So that's the situation that we have. The magnitude of M is going to equal FD sine theta, because this is FD when it's perpendicular. Now, for this particular problem, we got to do a couple of things. You may want to write down this trig identity. And I think the cosine is the one of these is the reverse. Cosine is like, if I do this, I get it. You want to double check my sign. I think you have to have it reversed. So check sign, because I'm pretty sure my notes are wrong. Because one of them, the plus and the minus, is not the same. You have a flip of the sign. But the whole reason we do that is this. That becomes 1, this becomes 0, and that just becomes cosine of theta. So for this problem, the force is just mg, negative. It's going to be negative 120 kilograms, 9.8 meters per second squared. Gives me 1176 newtons. Now we got D. So it's F D sine of the angle, which in this case we figured out that sine of my angle is actually cosine, so I'm going to get my 1176. That's a negative. My distance is 7.5 plus x, cosine of the angle. The negative means the torque is going that direction. So I got to keep track of my signs. Positive is counterclockwise. So I've got that. So that's the magnitude of the momentum. The maximum, of course, is going to occur when cosine is equal to 0, or cosine is equal to 0 degrees, which is cosine is equal to 1. So that implies 0 degrees. So the maximum occurs when D is the greatest. Or at 5 meters. So now we get M is equal to the magnitude of M is 1176, 7.5 plus 5, cosine is equal to 1, and the amount in the moment that we get is 14,700 Newton meters, and we know it goes that direction. And a lot of times what you're going to be doing is you're actually going to be drawing the direction of your torque.
For our angle, why did we have to add the 90 to our angle?
Why do we have to do it this way?
Couldn't we have just taken it from our horizontal axis, from our positive x?
Yeah, but then you end up not, the solution isn't as clean. Because I want to get to the cosine here. The solution, it just isn't as clean. All right, so we're gonna get this situation here. I've got a set of pipes here, or a set of bars. This is point B, and this is a 500 Newton force from B, and we're told this is a 5, 4, 3, we're told that's a 3, 4, 5 triangle at B. We're going to apply a force of 300 newtons here, and we're told that this is a 60-degree angle. This is a point A, and we're told that this is 2 meters, and this is 3 meters. And we're told that this is a 250 Newton force, and that's 30 degrees. Okay, we want to find, we want to determine the moment of each force about B. Okay, we want to determine the moment of each force about B. So, oh, and we're told that this is 4 meters. Okay. So, when you get a problem that looks like this, make life easy on yourself. If I'm looking at B, there's a lever arm from B to this one, right? I got a lever arm from B to that one, because that force is acting at 4 meters away. There's a lever arm from this one, because that force is acting over here. There's no lever arm at this one. That force is acting on a point. So the moment for the 500 Newton force is 0. Because if that moment is R cross F, R is equal to 0, R cross F, that equals 0. We all good on that?
Because it's acting on B, and B is.
There is no lever arm.
Yeah.
Lever arm's equal to 0. So I'm going to do this one up here. So I've got the force that's a 250 Newton force. I'm going to go ahead and write out its components. I'm going to actually do this one by the matrix method, all right? We'll find out we can do this a little shorter along the way, but I'm actually going to do this by the matrix method to start. So this is going to be my 250, and it's in the positive. This one's in the positive direction, but it's going to be, if that's 30, it's going to be sine of 30 degrees in the I, and it's minus 250 cosine 30 degrees in the J. And that works out to be 125 I minus 216 J. My lever arm, so let's look at my position vector. Okay, my position vector, that's negative 3I plus 4J. In this case, I want the position vector because the position vector is my lever arm. So this is equal to R. So I am going to do, my moment is R cross F, which is I, J, K. I have, my R goes up first, so I get negative 3, 4, 0. I end up with 125 minus 216, 0. And I'm going to go ahead and write out all the gory steps. So I get 4, 0, negative 2, 1, 6, 0, I, minus negative 3, 0, 125, 0, J, plus negative 3, 4, 125, minus 216, K, that's 0, that's 0. So I end up with negative 3 meters, negative 216 newtons, minus 4 meters, 125 newtons, all in the K direction. If I do the arithmetic, I get a positive 648 minus 500, and that gives me 148 Newton meters in the K direction. We good? So let's do the next one. Its R vector is a lot easier. R vector is 4J. So I'm going to just do this one. So this is R cross F2. I get my I, J, K. R is just 4. This one is negative 300 cosine 60 degrees. This one is 300 negative sine 60 degrees, and that's 0. That becomes I, J, K. And I get 0, 4, 0, 150, 260, 0. And we could write out all the gory details, but if I do the I got zeros and zeros, so there's a 0 in front of the I. I've got in my J, I got zeros and zeros, so there's zeros in front of my J. So I end up with the plus 0, 4 minus 150 minus 260 K. That's 0, so I end up with a negative 4, negative 150 K. That gives me 600 Newton meters in the K direction. Make sense? Until you do one, right? Until you do one. Okay. I will look at what we got in terms of